Usually when you think about a computer's memory, you think of it like a filing cabinet.
Yeah, exactly.
Yeah.
Like a physical drawer.
Right. You put a file in, you close the drawer, and then when you need it again, whether that's days or years later, you just open that exact same drawer, and the file is exactly where you left it. It's totally static. It's basically dead storage.
It's a completely passive repository. I mean, the machine doesn't care what the file actually means. It doesn't organize it while you sleep.
No, not
But
true.
it certainly doesn't rewrite it. It just holds those ones and zeros in this sort of magnetic stasis until you explicitly ask for them.
But then you step into the world of modern artificial intelligence. Specifically, for today's deep dive, and today is Friday, June 12th, 2026, we are looking at the cutting-edge Shannon Prime architecture.
Which is just a totally different beast.
It really is. The moment you open the documentation on this system, that entire filing cabinet metaphor it completely falls apart and burns to the ground.
It really does. It's a fundamental paradigm shift.
Because we are looking at a system that actively, relentlessly curates its own past. It decides what to keep, it decides what is just useless noise, and throws it away. And this is perhaps the most incredible part, it literally drafts multiple versions of its own future before it even speaks a single word to you.
Yeah, we are moving totally away from passive storage. We're entering the realm of this active, almost immune system-like memory management protocol. I mean, it is the absolute definition of a dynamic, self-managing cognitive architecture.
And that is exactly our mission for this deep dive. We've got this massive stack of developer logs, architecture contracts, raw engineering reports, all from the Shannon Prime XBAR memory system.
It's a lot of material to go through.
Oh, it's a mountain.
Yeah.
But our goal is to decode the exact mechanisms of this architecture for you. We're going to dig all the way down into the lowest level technical scenes of its C code.
Which is fascinating on its own.
Right. And we're going to examine this wild propose gate promote memory loop and explore how they are integrating this bleeding edge technology called diffusion gemma, basically to fast forward the AI's thought process.
It's an incredibly ambitious technical stack to unpack, for sure. But, if we want to truly understand how this cognitive architecture functions, we really can't start with those high-level concepts.
No, you can't start with the AI drafting its own future.
Exactly. You have to start in the basement. We have to look at the raw foundation of how data moves around inside the machine.
Right. Because before we can talk about how an AI curates its memories, we have to look at how it keeps those memories from leaking or corrupting or fundamentally crashing the entire system when all this massive data is shifting around.
And it is shifting in real time. Billions of operations.
So let's unpack this. We really need to talk about the L1 ABI.
The Layer 1 application binary interface. This is, without a doubt, the absolute bedrock of the Shannon Prime software architecture.
Okay, so to visualize this for you, imagine the software of this AI is split into two very distinct layers. On the inside, you have the Shannon Prime core.
The engine room.
Yes, the engine room. It's doing all the heavy, complex math, the tensor operations, the deep neural network processing, and it is written in C.
Which is very fast, but very dangerous.
Right. Then, wrapped around that engine room, you have the L2 layer. This is the control room, written in Rust. So the ABI is this strict boundary between the two layers. I actually like to think of this FFI boundary, the foreign function interface, like an incredibly strict international border checkpoint.
That is a very apt analogy, actually, because these two programming languages operate on entirely different philosophies. The C core, the L1, is a highly optimized, extremely dangerous environment. It handles raw, discrete algebra.
Okay, wait, pause right there. Discrete algebra. That sounds like math that's good at keeping secrets. What are we actually talking about in this context?
Right. So in high-performance computing, discrete algebra refers to mathematical structures that operate on distinct, separated values rather than a continuous spectrum.
Okay, like what?
We are talking about operations over finite fields, complex matrix multiplications, and things like Frobenius lifting.
Frobenius lifting.
Right. It's a way of mapping mathematical elements to specific powers in a polynomial ring. It's used to stabilize complex cryptography and these massive state transformations.
Wow. Okay, so heavy, heavy math.
Extremely heavy. And C is the perfect language for it because it provides bare metal, completely unconstrained access to the hardware.
It's fast.
It is unbelievably fast. But it is deeply unforgiving. I mean, if a developer mismanages even a single byte of memory in C, the entire process segfaults.
It just crashes.
Instantly, the program just dies.
Right. And then on the other side of that border checkpoint, you have the L2 Rust layer. And Rust is, well, it's famous in the programming world for its obsessive super strict memory safety rules.
It essentially refuses to let you compile code if it thinks there's even a fraction of a chance you might cause a memory leak.
Exactly. The L2 Rust layer is the safe zone. So this massive engineering challenge is basically how do you pass gigantic amounts of memory, the actual active thoughts of the AI back and forth across this border between a dangerous language and a safe language.
Billions of times a second.
Yeah, without losing track of who owns what. And the rule they established to solve this is fascinating. Going back to our international border analogy, L1, the C core, doesn't just hand out luggage full of memory that L2 has to be responsible for throwing away later.
No, not at all.
Instead, L2 brings its own completely empty suitcases, hands them across the border to L1, L1 packs them full of data, and L2 takes them back.
This is known as a strict caller-allocated memory ownership model. Every single buffer, every chunk of memory that crosses this hot path, which is the main active execution loop of the model, is allocated by the L2 caller.
So L1 never allocates it.
The L1C core never uses a standard memory allocation command, like malloc, for anything that L2 has to eventually free.
So the C core never says, hey, I just spontaneously created this new chunk of data for you. Here you go. Don't forget to delete it when you're done.
Never. Because, don't forget to delete it later, is the exact mechanism that causes memory leaks in high-performance computing.
Right. Someone always forgets.
Exactly. If the C core allocated the memory, the Rust wrapper would have to blindly trust that it knows exactly how and exactly when to call the C core's highly specific freeing functions. If the timing is off by a microsecond, the system bleeds memory until the server crashes.
So instead, the Rust layer says, here is a precisely sized empty buffer. I own it. You just fill it.
Exactly.
But wait, how does Rust know how big the suitcase needs to be before it even crosses the border? I mean, if the AI is about to generate a complex thought, how does the safe zone know the exact dimensions of that thought in advance?
That is managed right at load time. The exact moment the AI model boots up, the system executes a query against a specific structure called sparch info.
Okay.
This structure tells the L2 wrapper the exact rigid mathematical geometry of the model. It essentially says the vocabulary size of this specific AI is exactly 128,000 tokens. The hidden dimension is exactly 4,096.
Ah, so it gets the architectural blueprints right up front.
Precisely. So the L2 wrapper knows, without a shadow of a doubt, exactly how many bytes the logits buffer, which is the output probabilities of the next word, will require. It pre-allocates that exact amount of physical RAM, hands the raw pointer across the ABI border, and the L1 core just fills in the blanks.
It's incredibly clean.
Mm-hmm.
But reading through the developer logs, there are a couple of things that L1 does actually build itself, right? There are these two opaque objects that cross the border.
Yes, there are two distinct opaque types that cross the foreign function interface, the SPA model and the SPA session. L1 has to build them because only L1 truly understands their chaotic internal layout.
What's inside them?
We're talking about complex, quantized weight arenas, highly packed math structures that would make absolutely no sense to the Rust layer.
Okay, so L1 builds them, but does L1 own them?
No. And this is where the strictness of the boundary truly shines. Even though L1 builds them, their lifetimes are strictly governed by L2. L1 hands over these opaque handles, basically saying, I made this, here is the ID tag for it.
Right.
But L2 is strictly responsible for destroying them, and L2 cannot use a generic delete command. It must use specific, precisely matched destroyer functions to clean them up. A pointer is never directly freed by the L2 caller using a generic operating system command.
So it has to hand the object back to the specific L1 destroyer.
Yes, sir. Exactly.
So the border control isn't just about shuffling data buffers around. It's about the entire life cycle of the AI's active session. Every piece of memory has an absolute undeniable owner.
It has to, otherwise the system falls apart.
But here's where it gets really interesting to me. I want to talk about the cancel flag, because when you're reading through the architecture contracts, this specific little flag solves a problem that absolutely plagues almost every high-speed web server that tries to route requests to a massive AI model.
You are referring to the use after free error,
Yes.
commonly known as UAF. It is a catastrophic failure mode in computer science.
Right. So I want to paint a picture for you of why this is such a big deal. Imagine you're using a web interface to talk to this AI. You ask it a highly complex question. The server receives your question, spins up a worker thread, and the AI starts doing the heavy math to generate an answer.
It's actively grinding through the tensors.
Exactly.
Yeah.
But then halfway through, you realize you made a typo. So you slam the stop generating button, Or maybe you're on a train and your cell connection just drops completely.
That happens constantly in real-world deployment.
So the server needs to cancel that massive mathematical computation immediately, right? Otherwise, it's just burning incredibly expensive GPU cycles for a user who isn't even there anymore.
The computation must be aborted cleanly and instantly.
So in a naive software design, how would a system try to handle that cancellation?
In a traditional, perhaps less rigorous design, the L1 core, the one doing the actual math, would create a cancellation handle, basically an abort switch. And it would give that switch to the L2 wrapper.
Okay.
So now you have two concurrent processes running. You have the worker thread deep in the C core, actively running the AI model and generating tokens. And you have the handler thread up in the web server layer, actively listening to your HTTP connection.
Right.
If you hit cancel, the handler thread reaches down, grabs that cancellation handle, and tries to flip the switch to tell the worker thread to stop.
But what happens if the timing is microscopically wrong? What if the worker thread just finished the job naturally, closed the session, and completely destroyed that cancellation handle a millisecond before the handler thread tried to flip the switch?
That is the nightmare scenario right there. If that happens, the handler thread reaches down and tries to access a specific memory address that has already been freed and returned to the host operating system.
Oh, wow.
That is what a use after free error is. It's a dangling pointer dereference. The program thinks there is a switch there, but the switch is gone, and that memory might now belong to a completely different application.
That sounds dangerous.
It is. Best case scenario, the program recognizes the violation, instantly segfaults, and crashes the entire server. Worst case scenario, it silently corrupts other memory or creates a severe security vulnerability where arbitrary code can be executed.
It's like trying to pull the emergency brake on a train, but the train has already arrived at the station, been disassembled, and you just yanked a lever connected to nothing, and the whole station collapses.
That's a good way to look at it.
So how does Shannon Prime actually solve this? The documentation mentions a concept called inverted ownership.
It is a brilliantly simple piece of engineering. Instead of the L1 core owning the cancellation handle and giving it to L2, Shannon Prime uses an arcatomic bool that is owned entirely 100% by the L2 Rust wrapper.
Okay, arcatomic bool. That is some heavy Rust jargon. Let's break that down for everyone.
Certainly. ARC stands for Atomic Reference Counted. It is a specific type of smart pointer used in Rust. It provides a mathematical guarantee that the memory it points to will stay alive and perfectly valid as long as any part of the program is still holding on to a reference to it.
So it's keeping track.
It counts how many people are looking at it, and it absolutely refuses to be deleted until that count hits 0.
Okay, and the atomic bool part.
Inside that arc is an atomic bool. This is just a simple true or false flag. But it is atomic, meaning it can be safely read and written to by multiple different threads at the exact same microsecond without locking up the system or causing a data collision.
So in practice, L2 creates this incredibly safe flag. It sets it to false meaning, don't cancel, everything is fine. It then hands a raw, read-only pointer to that flag across the border to L1.
Precisely. L2 owns the memory entirely. L1 merely reads it. As L1 is grinding through the massive tensor math at every single layer boundary of the neural network, L1 takes a tiny microscopic pause to peek at that memory address.
Just a quick check.
Right. It simply asks, is the flag true yet? If it's false, L1 dives right back into the math. If it's true, L1 immediately stops what it's doing, unwinds its current step cleanly, and returns an error code back across the border saying the session was aborted.
And because L2 is the sole owner of that arc, even if the handler thread and the worker thread get completely chaotically out of sync, the memory address L1 is peeking at is mathematically guaranteed to be valid.
Yes. The arc ensures the memory won't be freed until both the session wrapper and the cancel wrapper are completely destroyed.
Okay, I see.
Think about the race condition we described earlier. Say the user disconnects. The handler thread sets the flag to true, but let's say the session was already over. In this inverted model, setting the flag to true is just a completely harmless write to a piece of memory that nobody is reading anymore.
The memory's still there, it's just ignored.
Exactly. The UAF window, that dangerous millisecond of overlap, is completely, totally eliminated by simply inverting who owns the flag.
It's like L2 gives L1 a walkie-talkie and says, just keep listening to this channel, I'll tell you if we need to abort. L1 never has to worry about the walkie-talkie batteries dying or the device magically vanishing into thin air. It just listens.
It is such an elegant solution to a notoriously ugly computer science problem.
It really is. And this rigorous, obsessively clean approach extends to how they handle errors across that border, too.
Oh, it has to. They ABI error codes. They aren't just generic, error 500, something went wrong, please restart.
Right. You don't just get a sad face emoji on the screen.
Far from it. The error codes in Shannon Prime are highly specific, and they map directly to the underlying mathematics of the system. They name discrete algebra failures.
So what does that look like?
Well, if something goes wrong in the L1 core, you might receive a VHT2 error. That specifically points to a mathematical failure in the cyclotomic ring transformations. Or you might get a spine or decompression error, which explicitly means a compressed block of mathematical memory was corrupted during readback.
From a developer's perspective, I have to imagine that is an absolute godsend. You aren't guessing why the math failed. You aren't hunting through millions of lines of code to find a bug.
No, the core is literally screaming at you, hey, this exact algebraic property was violated at this exact moment.
Let me push back on this a bit. I understand how safe Rust is, and I understand inverted ownership, but we're talking about an AI generating massive amounts of text, saving gigabytes of memory, doing infinitely complex math. What happens when the physical machine just simply runs out of room? Are all memory errors treated as fatal? Because if the whole border checkpoint just shuts down every time the hard drive gets full, that doesn't sound very dynamic to me.
That is an excellent question, and it highlights a crucial fundamental distinction the architecture makes. There are two very different out-of-memory scenarios, and the system treats them with entirely different philosophies.
Okay, lay them out.
The first error code is SPENUM.
Which sounds very bad. Error, no memory.
It is the worst-case scenario. It is a hard, fatal failure. SPENUM means the host operating system's actual physical RAM is completely exhausted. The memory allocator literally reached into the computer and returned an NLL pointer.
Oh.
When that happens, there's absolutely nothing the software can do to save the process. The physical hardware is tapped out.
Game over. The machine has no more physical space to think.
Exactly. But the second error code is SPE contextful. This is entirely different, and it is not fatal at all.
Okay, contextful. That means the AI's context window, its short-term working memory, the amount of text it can actively keep in its head at one time, has hit its maximum allowed length.
Correct. The sequence position counter essentially hit the maximum context limit defined at load time. When the L2 wrapper receives SPE context full from the L1 core, it is not a crash. It is a signal.
A signal to do what?
It's a prompt for the developers who are building those L2 wrappers to actually take action. Specifically, it tells them to trigger a memory eviction policy.
And reading the documentation, they don't just delete the oldest stuff. It specifies a very specific rule for this eviction. Fibonacci subsampling eviction.
Yes. This is where the cognitive architecture starts to show its brilliance.
How so?
Well, if you use a standard cache system, what we call FIFO, first in, first out, when the memory gets full, you just chop off the oldest part of the conversation. But for an AI, that means it literally forgets how the conversation started, which degrades the quality of its answers over long interactions.
Right, it loses the plot entirely.
Instead, Shannon Prime uses a golden ratio retention policy. When the context is full, the system logically prunes the memory, retaining tokens at intervals based on the Fibonacci sequence.
Okay, let's visualize that. Why the Fibonacci sequence specifically?
The Fibonacci sequence naturally spaces things out logarithmically. By using it for eviction, the AI keeps a very dense, perfect memory of what you just said to it a few seconds ago.
Okay.
But as you go further back in time, the memory becomes sparser. It keeps the broad strokes, the overarching context of the beginning of the conversation, without retaining every single useless conjunction and punctuation mark.
Oh, that's clever.
It frees up logical space while maintaining the narrative arc. And then it simply reissues the generation call to the L1 core to continue thinking.
So SPENUM means the physical computer is dead, but SPE context full just means the AI needs to take a deep breath, summarize its past thoughts using this elegant mathematical pattern, and keep going.
Precisely. If the developers had lazily collapsed those two error codes into a single generic out-of-memory error, the L2 developers would have absolutely no way to implement that continuous generation eviction policy.
The strictness of the border control, the ABI, is exactly what enables the flexibility of the higher-level cognitive behavior.
Exactly.
Okay, so we have established that the border control is incredibly secure. Memory isn't going to leak, errors are perfectly categorized, and the entire system won't crash if a user on a bad cell connection hits cancel.
The suitcases are packed safely and securely.
Right. But that raises the obvious next question. What exactly are we putting inside those suitcases? If the AI isn't just storing text, what are we actually storing?
And this leads us right into the XBAR system and the architecture that holds the AI's actual active thoughts.
The technical documentation calls XBAR a token-free intermodal memory architecture, and it relies on two separate AI models sharing a space, an executive model and a Memo curator model.
Let's break down why that is so revolutionary. Most language models today, the ones the public interacts with, operate entirely on text tokens.
Right.
You feed them a transcript of a conversation, they turn those English words into mathematical vectors, process them through billions of parameters, spit out a single new word, and then they forget everything.
Wait, everything?
Yes. To get the next word, you literally have to feed the entire transcript plus the new word back into the system from scratch. It is wildly, staggeringly inefficient.
It's like having to reread the entire Lord of the Rings trilogy from page 1 every single time you want to turn the page to see what happens next.
That is exactly what traditional autoregressive models do. XBAR completely bypasses the text.
Oh.
The executive model is the main AI, the massive brain generating the responses for the user. As it thinks, layer by layer, it generates deep internal mathematical representations of concepts. These are called key value, or KV, states.
Okay.
XBAR takes those deep, latent mathematical states and stores them directly into a shared memory space called a cyclotomic ring.
Okay, I have to stop you again. Cyclotomic ring. We mentioned it earlier with the error codes. What is that visually? Because it sounds like something from a particle accelerator.
It is a complex mathematical structure. Visually, imagine a circular whispering gallery. In standard memory, data is stored in a linear line. In a cyclotomic ring, the mathematical vectors are arranged in a circular polynomial structure.
And what does that actually let the AI do?
This allows the system to perform highly complex rotational queries on the data. It means the AI can search its own memories by looking for mathematical resonances rather than just scanning a list top to bottom.
Oh, wow.
It makes the retrieval of latent thoughts incredibly fast.
Okay, so the executive model is pouring its raw, latent thoughts into this circular whispering gallery. And what about the Memo curator?
The Memo curator is a smaller, secondary, highly specialized AI model. It lives entirely in the background. It doesn't talk to the user at all.
So what's its job?
Its entire existence is dedicated to looking at the memory ring that the executive is filling up and managing it. It decides what is important. It compresses long thoughts into shorter gists. It merges redundant ideas, and it evicts useless noise.
And they share this space.
Yes, they share this latent space, communicating entirely in mathematics, completely token-free.
It sounds perfect in theory, but when the Shannon Prime developers actually surveyed their own code base to see how this two-ring architecture was operating in reality, specifically when they were running it on the Qwen 3 CPU setup, they found some massive, completely non-obvious hurdles.
They did.
They did a deep technical seam analysis and came back with 3 major findings that completely upended their design.
Yes. These 3 findings radically reshaped how they had to build the entire memory curation loop. Finding number 1 was perhaps the most jarring discovery.
What was it?
They realized that the 2-ring memory was naturally per decode ephemeral.
Okay, reading that in the notes was wild to me. Let me make sure I understand this. It's like a person having a brilliant realization, an absolute earth-shattering epiphany, but their brain completely physically evaporates the memory of it the exact moment they finish speaking the sentence.
That is essentially what was happening at the code level. The core functions, specifically Qwen 3 generate KV and Qwen 3 PPL decode, were operating exactly as originally programmed.
Doing what they were told?
Right. They would build the memory ring, store the KV states, generate the output text for the user, and then as soon as the function finished, the C core would instantly free all that memory and return it to the system.
So it just vanished.
Absolutely vanished. There was absolutely no automatically persisted episode object for the Memo curator to operate on between sessions.
So the main brain was vaporizing its own dream journal before the background curator could even pick up a pen and start organizing it.
Exactly. And the entire premise of having a memory curator fundamentally requires that there is actually a stored state to curate between active sessions. Finding 1 confirmed that episode persistence wasn't just a nice-to-have feature they could add later.
It was required.
It was an absolute prerequisite that had to be engineered from scratch. The system had to be taught how to hold on to a thought after it was done speaking.
Which brings us to finding 2. And this one seems like it saved their lives from a computational hardware standpoint.
What is truly fascinating about Finding 2 is how it addressed the router index, known in the codebase as poke.
Right, because if the AI is going to recall a specific memory from that circular whispering gallery, it needs an index to look it up, just like the index at the back of a massive textbook.
Exactly. But in a high-dimensional AI architecture, the index is vastly more complex than a list of page numbers. The AI uses what is called a frozen Rademacher projection.
Okay, explain Rademacher projection.
A Rademacher projection is a mathematical technique used to reduce the dimensionality of data while preserving the distances between the data points. Essentially, it multiplies the complex memory vectors by a matrix of randomly generated ones and negative ones.
Okay, so it compresses it.
It creates a compressed mathematical fingerprint of every memory state so the AI can quickly search for relevant past thoughts without having to read the entire memory file. The problem is, this index, proc, is massive.
How massive?
If you have a long conversation with the AI, saving that complex mathematical index to a physical hard drive would require gigabytes of data. It would cause a catastrophic serialization bottleneck.
Meaning it would literally take too long to save it to the hard drive and too long to load it back up into RAM when the AI wakes up. The user would just be sitting there watching a loading spinner.
Precisely. But Finding 2 was a breakthrough. The developers realized that the router index, proc, is entirely recomputable. You don't need to save the massive index at all.
Because the Rademacher projection is frozen. It's deterministic.
Exactly. Because the mathematical matrix of ones and negative ones is frozen and deterministic, it never changes. As long as you save the raw K vectors, the actual underlying memory data, you can simply rebuild the index on the fly the moment you load the memory back into active RAM.
Oh, that's smart.
You just run the stored K vectors back through the frozen projection. This meant a persisted episode only needed to be the raw K store, a raw V store, and a tiny, lightweight manifest file. They completely, elegantly sidestepped the serialization bottleneck.
It's like realizing you don't need to keep a massive, heavy printed index of a giant library because you have a lightning-fast algorithm that can instantly generate the index from scratch the exact moment you walk through the library doors.
A perfect parallel. It was a massive win for efficiency. But then they hit Finding 3, and Finding 3 was a double-edged sword that almost broke the system.
What did Finding 3 say?
It states two things. First, that eviction is doubly entangled, and second, that the standard Studio file store truncates upon opening.
Okay, let's translate that. Eviction means the memo curator deciding to throw a useless memory away. Why is it doubly entangled?
It loops directly back to that recomputable index we just discussed. If the curator decides a specific memory is useless noise and drops it from the physical hard drive store, the active system doesn't automatically know that happened. The active router index still holds the fingerprint of that memory. It still thinks the memory is there.
Yeah, it sounds like a problem.
It is. So a curator that wants to evict a memory must meticulously prune both the physical hard drive store and the active in-memory index simultaneously to maintain consistency. If they get out of sync, the AI tries to recall a memory that no longer exists, and the system panics.
Okay, that makes total sense. It's a synchronization issue. But what about the second part of Finding 3? The Standio store truncates upon opening. What does that actually mean in plain English?
It exposes a fundamental flaw in how the default C code was handling file operations. The command used to open the memory file on the physical hard drive was utilizing the W+B flag.
Okay, what does that flag do?
In the C programming language, opening a file with W+B means open this file for reading and writing, but if the file already exists, completely wipe it clean first.
Wait, what? It truncates it. It deletes absolutely everything inside it.
Exactly to 0 bytes. The current decode path literally could not load a pre-curated store.
Oh my God.
Imagine the scenario. The Memo curator spends hours offline during the night, meticulously organizing, compressing, and perfecting the AI's memories into a beautiful, streamlined episode.
Right.
But the exact moment the executive model wakes up to answer a user's prompt and opens the file to read those memories, the W+B flag accidentally deletes the entire thing.
The curator is standing there saying, "Here is your highly organized dream journal. I worked on it all night." And the executive opens a cover, and all the ink instantly evaporates off the pages.
Precisely. It was a functional dead end. To ever replay a curated episode, they fundamentally needed to invent a non-truncating load path. They needed a way to open the book and read it without the act of reading erasing the ink.
Which perfectly sets the stage for how they solved it, because the memory naturally evaporates. Finding 1 and the default code erase files upon opening them. Finding 3, the engineers were backed into a corner. They had to invent a way to artificially resurrect the past. They had to build the tools for the AI to actually hold on to its history.
And that brings us to the concept of replay decodes and the C1 Lite transactional loop.
And replay decodes.
They are the crucial, foundational, enabling capability for this entire cognitive architecture. Without them, there is no memory, there is no curation, there is no Shannon Prime as we know it.
So what exactly is a replay decode? How does it fix the disappearing ink?
The engineering team created a completely new system flag called SP Replay. This flag establishes the non-truncating load path they so desperately needed. When the AI boots up for a new session, instead of starting with a blank slate or wiping the memory file with the old C command, SP Replay safely, carefully opens the persisted historical KV data from the hard drive.
It opens the book without erasing the pages.
Exactly, but it goes much deeper than just reading a file. It takes this historical mathematical data and injects it deep into the AI's neural network, specifically right after a computational step called the ROPE layer.
Okay, the ROPE layer. Let's define that for the listener because that sounds important.
ROPE stands for rotary position embedding. In a neural network, the model doesn't natively understand the order of words. It doesn't know that the dog bit the man is different from the man bit the dog unless you give it positional information.
Got it.
The ROPE layer acts as the AI's internal compass for sequence. It mathematically rotates the data so the AI knows exactly where every concept belongs in time.
Okay.
By injecting the historical memory data right after the ROPE layer, the SP Replay command essentially bypasses the normal linear input processing. It forces the model to seamlessly remember a past session as if it had just organically thought of it a millisecond ago.
That is wild. It's a literal inception mechanism. You aren't just handing the AI a text transcript to read and analyze. You are loading the raw mathematical feeling of the memory directly into its active processing pathways.
The mathematical feeling of the memory is a highly poetic way of describing a deep tensor injection, but from a functional standpoint, you are exactly right. The model consumes the loaded history seamlessly, and once you have proven that capability, once you have the ability to persist memory safely and replay it flawlessly, you can finally build the Memo curator. You can build what they call the C1 Lite transactional loop.
I love how the documentation describes this loop. They call it the AI's memory immune system.
It's a very fitting name.
It's not just a dumb filing clerk putting papers in folders. It's an active immune system relentlessly testing and defending the integrity of the memory. And it operates on a very strict three-step cycle: propose, gate, promote.
We need to examine how this works in detail because it is a beautifully rigorous piece of computer science. It ensures that the AI's memory can never degrade over time. Step 1 is propose. The Memo curator looks at a raw, bulky episode of memory and proposes a curated version. This proposed version is called a shadow episode. It exists parallel to the real memory. In this shadow episode, the curator might have merged some redundant vectors, or it might have deleted some completely irrelevant noise to save space.
It's a draft. The curator says, hey, I was looking at this 10-page memory, and I really think we can compress it down into 2 pages without losing anything actually important.
Right. But crucially, the system does not just blindly trust the curator's draft. That leads us to step 2, gate. The system must actively test the proposed shadow memory to ensure no vital details were lost in the compression. It does this by testing the perplexity delta, or PPL, and checking for absolute sequence identity.
Okay, let's unpack sequence identity, because this is the core of the immune system.
The test is brutal and absolute. The system takes the main executive AI and forces it to generate a specific deterministic output based on the original uncompressed 10-page memory. It records that output perfectly. Then it hot swaps the brain. It unloads the original memory, loads in the curator's proposed 2-page shadow episode instead, and asks the AI to generate the exact same output.
So if the compressed memory is good, if the draft is accurate, the AI should say the exact same words.
It must be bit identical, not just similar, identical. If the AI deviates even slightly, if it outputs a different token, or even if its perplexity, its mathematical confusion level regarding the next word spikes beyond a tiny threshold, the gate instantly triggers an alarm.
The immune system detects a pathogen. The proposed memory has been corrupted.
Exactly, which leads directly to step 3, promote or rewind. If the shadow episode passes the gate perfectly, producing the bit identical output, the system promotes it. It confidently overwrites the bulky original memory with the clean, compressed version.
And if it fails?
If it fails the gate, the system instantly triggers a rewind. It incinerates the shadow episode and leaves the canonical original memory entirely untouched.
It is a zero-risk curation loop. You literally cannot corrupt the AI's core memory because the math simply won't allow a degraded memory to be promoted.
That's the beauty of it.
And we can see this loop perfectly in action in the developer logs when they tested the cold-to-vic heuristic.
Yes, the cold-to-vic test is the definitive proof that this C1 light loop actually functions on real chaotic data.
So to set this up, cold-to-vic uses LRU telemetry. LRU stands for least recently used. It is essentially the AI keeping strict track of which memories it actually actively thinks about.
Correct. As the AI generates text, its internal attention mechanism is constantly scanning its memory ring for relevant context. The engineering team specifically instrumented the router to count hits, meaning they tracked exactly how many times the AI's attention mechanism actually pulled a specific memory position into its active thought process.
They built a massive histogram of these hits.
Basically a heat map of the AI's memories. Some memories are blazing hot, constantly being referenced. Some are just ice cold.
Okay, so they saw a gradient.
Precisely. And they found a very clean content recall gradient. Some positions had 36 hits. They were vital. But some positions had absolutely 0 hits. They were completely ignored by the attention mechanism from the moment they were created.
So they tasked the curator with a cold-to-vic. The curator proposed a shadow episode where it simply deleted all the 0-hit positions to shrink the file size, and then it rebuilt the index.
And then they gated it.
Now, I have to step in here and play devil's advocate. I want to vigorously push back on this philosophy. We are talking about deleting memories just because the AI hasn't thought about them lately. But think about human psychology. Humans have repressed memories or deeply buried memories that we might not think about for years, but they are absolutely vital to our psychology and our decision-making.
That's a fair point.
What if that 0-hit memory is something incredibly crucial that just hasn't come up yet? What if the user gave the AI a password or a launch code at the beginning of the conversation, and the AI hasn't needed to recall it yet? If it deletes it, isn't the AI basically lobotomizing itself for the sake of hard drive space?
That is a very profound and entirely valid philosophical fear. And it is the exact field that the mathematical gating mechanism is designed to address. Remember, the system doesn't just delete it and hope for the best. It gates it.
Right.
When they ran the perplexity gate on that cold evicted shadow episode, the output sequence remained completely 100% bit identical. Why? Because mathematically, if a 0-hit position has never won the attention router's top case selection pool, removing it from the pool of candidates changes absolutely nothing about the final mathematical output.
Okay.
If the password was truly vital, the attention mechanism's latent math would have at least registered a microhit on it when scanning for context. Because it registered 0, the memory was provably mathematically useless noise. The curator promoted the shrunk episode safely without lobotomizing anything.
Okay. The math proves it was useless. But I imagine they didn't just stop there. To prove the immune system works, you have to try to actively break it.
If we connect this to the broader philosophy of software testing, testing the failure state is the only way you prove the immune system actually functions. They intentionally forced a hot evict.
What do they do?
They maliciously told the curator to delete the single most recalled position in the entire memory, the memory with 36 hits.
They intentionally cut out a vital organ.
Yes. They deleted the vital memory, rebuilt the index, and ran the gate. Immediately, the generated sequence diverged. Without that vital context, the AI started outputting entirely different text.
The immune system kicked in.
The gate caught the error instantly, flagged the unacceptable perplexity delta, and triggered an emergency rewind. The corrupted shadow episode was deleted, and the canonical memory was preserved perfectly. The immune system conclusively proved it could catch aggressive, damaging amnesia before it became permanent.
It's phenomenal. It is a mathematically proven, ironclad way to let an AI sleep, dream, prune its own neural pathways, and wake up sharper without ever risking brain damage.
It's a huge step forward.
But, and there is always a massive but in software engineering, all of this beautiful, elegant C1-like memory logic was built and proven on the Qwen 3 CPU architecture.
Which is a very stable, very uniform, highly predictable environment.
Exactly. It's a nice, safe sandbox. But to move into the future, to actually deploy this on flagship hardware that millions of people will use, it needed to be ported to the Gemma 4 architecture. This is known in the logs as the P3 port. And plugging this new, incredibly complex Gemma 4 brain into this memory system revealed some serious, gnarly anatomical differences. The sandbox was gone.
The P3 architectural gaps. When the engineering team ran a pre-flight audit of the Gemma 4 internal geometry, the reality check was severe. They realized that transferring the XBAR memory system wasn't going to be a simple copy-paste job. Gemma 4's internal structure is wildly, fundamentally different from Qwen 3's.
The audit identified 3 major architectural gaps. Let's walk through them, starting with gap 1. The router needs per-layer class geometry.
In the older Qwen 3 architecture, the memory geometry is completely uniform. Every single layer of the neural network looks basically the same. It's a straight pipe, so the memory router could use a single global shape for its index.
Okay.
But Gemma 4 uses a highly aggressive hybrid approach. It alternates between SWA layers and global layers.
The SWA standing for sliding window attention.
Correct. SWA layers are designed to be myopic. They only look at very recent context to save processing power. They have a specific rigid shape, specifically 8 kV heads with a dimension of 256. But interspersed among these narrow SWA layers are global layers.
And what do they do?
A global layer looks at the entire history of the context, zooming all the way out, and it has a completely different structural shape. 1 kV head with a massive dimension of 512.
So the AI's internal pathways are constantly changing sizes. It's like trying to run high-pressure water through a plumbing system where the pipes suddenly double in width and then violently shrink back down over and over again through the whole house.
Exactly. The memory router index, proc, and the selection algorithms had to be completely rewritten from the ground up to carry per-layer class geometry. If they tried to force a single global shape through that variable plumbing, it would completely corrupt the data.
And if that plumbing nightmare wasn't enough, they immediately hit gap 2, shared KV layers. And reading this part of the report honestly hurt my brain a little bit.
It is a very aggressive optimization technique used by the Gemma 4 designers to save VRAM video RAM on the graphics card. In a standard traditional model, every single layer of the network creates and stores its own key and value memories as it thinks.
Right.
But in Gemma 4, some of the deeper layers don't mint any KV memory at all.
They don't create new memories, even though they are processing data.
They reuse the exact memory minted by an earlier owner layer. They literally share the physical memory space to save room on the GPU.
So how on earth does the Memo curator deal with that? If its entire job is to back up the memory layer by layer.
If the curator blindly scans down the line and tries to read the memory from a shared layer, it will pull absolute garbage because the memory doesn't actually exist at that address. It's a ghost.
Wow.
The curator had to be explicitly taught how to owner indirect.
Owner indirection.
Yes. When the curator scans a layer and detects that it is a shared layer, it must recognize a specific flag, completely skip its own extraction process, and redirect its read query back up the chain to the earlier layer that actually owns the physical data.
That sounds complicated.
The episode manifest had to be heavily upgraded to include an owner map, essentially a skip list. So the memory ring knew exactly which layers were real physical data and which were just echoes.
It's like trying to pack up a giant house to move, but you suddenly realize half the furniture in the house are just holograms projected from the living room. You have to have a map that tells you where the real couch is so you don't try to put a hologram in a cardboard box.
That is a highly accurate, if slightly surreal, visualization of the problem.
Okay, so that's 2 gaps.
And finally, they had to solve gap 3, conflicting window policies. We mentioned earlier that Gemma 4's SWA layers have their own native sliding window. They have a hard-coded limit on how far back they look.
Right.
But the XBR memory ring also has its own ring 1 window policy, which dictates what stays in the blazing fast RAM and what spills over to the slower Optane disk drive.
So you essentially have 2 different managers aggressively trying to organize the same office. One manager is deciding what's allowed on the desk, and the other manager is deciding what goes in the filing cabinet, and they aren't talking to each other.
Exactly. The interaction between the model's native SYA window and the memory system's ring window was entirely untested and prone to catastrophic collisions. Furthermore, those global layers, the ones that look at absolutely everything, are 75% unroped.
Meaning they lack that rotary position embedding we talked about earlier. They lack absolute positional encoding for most of their dimensions.
Correct. Because they lack that positional encoding, they require a completely separate recall policy compared to the SWA layers. The memory system literally had to be bifurcated. It had to be split in half to handle these 2 fundamentally different attention spans simultaneously without cross-contaminating the math.
Okay, so the internal anatomy of Gemma 4 is a complete nightmare to integrate with. They had to rebuild the plumbing, map the holograms, and fire one of the office managers. But before you can even begin curating these highly complex memories or speculating on the future, there is a massive fundamental hurdle right at the front door.
The tokenizer.
The very alphabet the AI reads has to be meticulously translated. We need to talk about the Gemma 4 tokenizer dispatch logic.
Ah, yes. The 514K merge BPE. This is a crucial foundational layer that is almost always overlooked by the public, but it is the source of endless headaches for engineers. A neural network does not read English. It doesn't read French or Mandarin or code. It only reads numbers token IDs.
Right, it's all math.
The tokenizer is the dictionary that translates human text into those specific numerical IDs.
And Gemma 4's dictionary is absolutely massive.
Massive and highly idiosyncratic. It uses a byte pair encoding, or BPE, with exactly 514,000 specific merges. But it doesn't operate on raw bytes like the older GPT-2 style tokenizers did. It operates over a very specific Unicode space, literally replacing standard spaces with a specific Unicode block character. And it uses a split pre-tokenizer based on extremely complex, highly specific regular expressions.
So it pre-slices the text based on punctuation and spaces before it even bothers to look up the words in the dictionary.
Exactly. And the Shannon Prime architecture standards required maintaining absolute strict compatibility with this across their entire ecosystem. They couldn't just swap in a faster generic tokenizer library off the shelf.
Because if the dictionary is wrong, the AI goes completely insane.
And precisely, if the generic tokenizer translates the word apple into token ID 400, but the neural network's weights were trained for months thinking token ID 400 means car, the math will execute perfectly.
It won't crash.
The system won't crash, but the output will be utter inexplicable nonsense. We call this silent hallucination. The system doesn't know it's broken, it just lies to you confidently.
Here is where I was reading the developer logs and I physically stopped. I realized the bottleneck they were facing. How did they solve the speed problem here? Because searching a dictionary with 514,000 entries every single time the AI reads or writes a single word sounds painfully, impossibly slow.
It is. You cannot use a linear scan. You cannot check entry 1, then entry 2, then entry 3. That would grind the entire supercomputer to a halt just trying to read the letter A.
So what do they do?
The engineers had to implement a specific U64 hashed rank table. It mathematically converts the adjacent text pieces into a 64-bit integer key and then performs a constant time hash lookup to find the lowest merge rank instantly.
That sounds much faster.
It completely bypasses searching. It requires an 8-megabyte table to be built in active memory the exact moment the model loads, but it makes the tokenization process lightning fast.
And they added a hard failsafe to this, right? The GMA4BPE family tag.
Yes, to prevent those silent hallucinations. The .speed tokenizer file gets physically stamped with a specific family tag, GEM-A4BPE. When the model loads into RAM, the very first thing it does is check this tag. If the tag is missing, or if it says anything else, the system throws a hard, loud error and absolutely refuses to run.
It loudly, violently fails rather than silently mistokenizing data.
Exactly. It forces the developer to acknowledge the mismatch and fix it, completely preventing the silent hallucination failure mode. It is a strict, uncompromising adherence to data integrity.
I love that. The AI literally says, I refuse to read this book until you give me the exact right pair of glasses. Okay, let's take a breath and synthesize where we are.
Good idea. We've covered a lot of ground.
We have established the baseline. We know exactly how the system safely reads the data with the hash tokenizer. We know how it rigidly protects its memory boundaries with the L1 ABI and the inverted ownership of the cancel flag. We know how it curates its past using the XBAR cyclotomic rings and the brutal proposed gate promote immune system. And we know how it handles the twisted holographic anatomy of the Gemma 4 GPU architecture.
All of that just to get to a stable starting point.
Right. Now, what sequence of events takes us from this baseline, this C1 light validation of the past, all the way to the bleeding edge? How do we go from an AI that manages its past to an AI that predicts its own future? This brings us to the roadmap. Fast-forwarding thought.
The sequence from the C1 light validation to the final diffusion lean integration is a very deliberate, step-by-step escalation of computational capability. It is the literal roadmap of Shannon Prime's ultimate ambition.
Let's walk that path. It doesn't happen all at once. It starts with C1 light.
C1 light is what we've been discussing. The heuristic loop running on the safe Gwen 3 CPU. It exists solely to prove the control flow, The propose, gate, promote logic using simple, human-coded rules like cold eviction based on LRU telemetry.
Okay.
It proves mathematically that you can safely edit memory without causing brain damage.
Once that was proven, they moved to P3.
P3 is the physical ring wiring on Gemma 4 using massive COD GPUs. This is where we solve the SWA versus global layers, the shared KV gaps, and actually wire the two-ring memory system into the massive high-speed graphics cards required to run flagship world-class models.
So C1 Lite proves the logic, P3 fixes the plumbing on the heavy hardware. Once the plumbing is fixed, we hit P2.B.
P2.B is where the system gets smart. It introduces cloud training. We replace the simple human-coded heuristic cold evict rules with a fully learned span compression adapter.
What?
This is an entirely separate AI trained specifically to compress N tokens of memory into a tiny K token gist, mathematically maximizing information density. It learns how to compress concepts rather than just indiscriminately deleting things that haven't been used recently.
It's the difference between an intern crossing out paragraphs with a black marker to save space and having a brilliant, world-class editor rewrite a rambling chapter into a single devastatingly perfect sentence.
A very precise metaphor.
Wow.
And once that trained adapter exists and is proven, we reach C2, Memo V1.
Okay.
This is the full upper applied directly to the active ring state. The Memo curator is no longer a script. It is now a fully trained neural network managing the executive's memory in real time, holding constant fidelity checks to ensure those tiny gists can still answer complex questions perfectly.
And then the climax of the roadmap, the integration of the diffusion lane.
Yes. The culmination of this entire architecture, integrating diffusion Gemma as a draft source for speculative decoding.
Okay, we need to unpack this incredibly carefully because diffusion is a massive buzzword right now. When you, the listener, hear diffusion model, you probably instantly think of AI image generators like Midjourney or DALL-E. I want to be crystal clear, that is not what this is.
Correct. It is vital to separate those concepts. Image generators use continuous noise denoising. They start with literal static, TV snow, and gradually mathematically smooth it out over dozens of sets until a picture of a cat emerges. Diffusion Gemma does not do that. It is a text model, and it uses a process called discrete masked diffusion.
What is discrete masked diffusion? How does it actually work with text?
Imagine a complete sentence where every single word has been replaced by a blank underscore, a canvas of random placeholder tokens. The diffusion model doesn't generate the text left to right, one word at a time, like a standard autoregressive model does.
How does it do it?
Instead, it looks at the entire block of blanks simultaneously. It iteratively refines them all at once. In a single pass, it guesses words for every blank, locks in the tokens that make grammatical sense, and swaps out the bad ones across the entire block in parallel.
I picture it like the difference between a painter and a sculptor. A standard AI model is like a painter. It applies one brushstroke at a time, left to right, slowly building the image linearly. You literally have to wait for stroke 1 to dry before you can get stroke 2. It takes time.
That's a good comparison.
But discrete masked diffusion is like a master sculptor who has a magical ability to chip away at an entire massive block of marble all at once from every angle simultaneously. The head, the arms, the torso, the entire shape reveals itself simultaneously across the whole block in a fraction of the time.
That is an exceptional way to visualize it mechanically. And because it operates in total parallel, it is incredibly, unbelievably fast. It is what we call compute-bound, meaning it is only limited by how many raw calculations the GPU's tensor cores can do per second. It is not limited by the memory bandwidth bottleneck of having to fetch massive weight matrices from RAM for every single word sequentially, which is what slows down standard models.
And this brings us to the T8 drafter. Reading the architecture docs, they explicitly state that the T8 drafter is the absolute #1 priority placement for this new diffusion technology. Why?
Because it elegantly solves the biggest, most stubborn problem with speculative decoding.
Which is?
In speculative decoding, you use a small, fast, slightly dumb model to draft a bunch of text, and then you use the big, smart, slow model to verify it. If the draft is good, you just fast-forwarded the big model and saved a ton of time. But traditional small models often write terrible drafts, so the big model rejects them, rewrites it anyway, and you just wasted all the electricity running the small model for nothing.
But diffusion Gemma changes that math.
Entirely. Diffusion Gemma drafts an N-token block, say an entire paragraph of 256 words, incredibly fast using that parallel sculptor method. Then it hands that entire block of text up to the main, massive, autoregressive executive model. The executive doesn't read it word by word. It reads the entire block in one single parallel forward pass.
It verifies all 256 words simultaneously.
Yes. It converts what used to be a slow, memory-balanced sequential decode operation into a massive, compute-dense batch operation.
And this gives us what the source material calls zero-risk performance gains. I want you to explain the zero-risk part, because usually in computer science, incredible speed comes with a quality penalty. You trade accuracy for latency.
This is the genius of the T8 MTP protocol. The verification done by the heavy executive model is strictly byte exact. It mathematically compares the draft paragraph against what it would have generated itself if it had been thinking normally. If the draft matches perfectly, the entire sequence is accepted instantly. If the draft is wrong, even slightly, even by a single comma, the system executes an O of 1 watermark rollback. It instantly rewinds to the exact mistake and takes over manually from that point forward.
So a bad draft never, ever makes it to the user's screen.
Never. A bad draft only hurts the speed, the hit rate of the speculation. It never degrades the final output quality. The user gets the exact same high-quality intelligence of the massive executive model, but potentially 4 times faster if the diffusion drafter is having a good day and predicting accurately. It is pure latency reduction with an absolute, unbreakable mathematical guarantee of quality.
That is it's mind-blowing. It's an AI thinking ahead of itself, predicting multiple versions of its own thoughts, and verifying them in a fraction of a second before the user even blinks. But seeing those speed numbers makes me wonder something. If this T8 drafter is so incredibly powerful, and diffusion Gemma is this parallel processing sculptor that's 4 times faster, why isn't it being used for absolutely everything? Why not just make the entire AI a diffusion model and throw away the old, slow, auto-regressive architecture completely?
Which brings us to the final piece of the puzzle, priorities and physics. The cold, hard reality of computer hardware.
The documentation compares the placement priorities of 2 different instruments. The T8 drafter is explicitly priority 1.
Yes, because it directly accelerates the hot path. The hot path is active generation. The user is sitting at their screen watching a cursor blink, waiting for an answer. The T8 drafter drastically reduces that waiting time. It is a direct, highly visible upgrade to the user experience. It justifies its existence instantly.
But there is a priority 2, the GR3 LASS instrument. And this is a completely different beast.
Priority 2 is strictly for consolidation time. It operates entirely offline during what the developers call the night T-shift loop, when the user is asleep and the AI is quietly managing its episodic memory in the background.
What does GR3 LAS actually do?
It acts as the ultimate, unforgiving gatekeeper before a memory is permanently compressed. Remember the P2.B adapter we talked about? The brilliant editor that compresses a 10-page memory into a tiny K-token gist?
Right.
Before the system allows that compression to become permanent and before it throws away the bulky original memory to save hard drive space, the GR3 loss instrument steps in. It takes that tiny compressed K-token gist, and it uses the diffusion infilling mechanics to attempt to conditionally reconstruct the verbatim ring-2 memory from it.
It tries to expand the one perfect sentence back into the full 10-page chapter.
Yes, and then it measures the exact loss of information. It calculates the mathematical delta between the original memory and the reconstructed memory.
Wow.
This provides a mathematically bounded loss coefficient. It proves, with mathematical certainty, exactly how much detail was permanently lost in the compression process. If the loss is within an acceptable threshold, the memory is permanently compressed. If the loss is too high, meaning the just lost vital context, the memory remains uncompressed.
It aggressively prevents the AI from confidently fabricating its own history. It won't let it summarize a memory if the summary fundamentally corrupts the core facts of what happened.
Exactly. It is a rigid mathematical safeguard against hallucination and long-term memory drift.
Okay, so we have these 2 incredible tools, T8 for drafting the future and GR3 LSS for securing the past.
Yeah.
But here is the massive warning label I've been holding on to. The design document has a huge red flag warning about hardware honesty and a specific testing rig called Beast Canyon.
Oh, yes.
If diffusion Gemma is so fast, why are they warning developers about it?
The hardware bandwidth limits. If we connect this entire architectural marvel back to the bigger picture, software architecture can only push as far as the physical silicon allows. Diffusion Gemma is a 26 billion parameter mixture of experts model.
That is huge.
It is massive. It requires 18 gigabytes of VRAM just to load the quantized weights into memory before it even starts thinking. The documentation boasts up to 4x speedups, yes, but those figures were achieved on a cluster of thousands of H100 GPUs. dedicated million-dollar enterprise-tier silicon.
Supercomputers.
Yes. But Shannon Prime's core development ethos is built on consumer-tier accessibility. They want this architecture to eventually run locally, so they test heavily on a rig called Beast Canyon, which runs an older RTX 2060 graphics card with 12 gigabytes of VRAM.
A completely standard, older gaming graphics card.
Precisely. And on the RTX 2060, the performance of diffusion Gemma absolutely tanks. It falls off a cliff, the 4x speedup vanishes, and it actually becomes slower than not using it at all.
Why? If the underlying math is exactly the same, if the software is perfectly written, why does the speed drop so drastically just because the card is a few years older?
Because of the SIM75 weak tensor ALU and severe memory bandwidth limits.
Okay, translate the hardware jargon for me.
The Turing architecture, which the RTX 2060 uses, lacks the advanced tensor cores required to do massive parallel matrix multiplication efficiently. Remember the sculptor analogy. The master sculptor chipping away at the whole block of marble all at once.
Yeah.
To do that, to execute that parallel diffusion pass, the GPU needs to perform an astronomical number of calculations simultaneously, what we call high arithmetic intensity. The Enterprise H100 can do it easily, but the RTX 2060 cannot. Its ALU, its arithmetic logic units, the actual tiny calculators inside the chip are too weak.
I see.
And more importantly, the memory bus that feeds data to those tiny calculators is too narrow. It simply cannot move the data fast enough to keep the parallel calculations fed.
So instead of a master sculptor with a giant chisel, it's a sculptor with a tiny little pickaxe trying to hit the whole block at once, and it just gets hopelessly bogged down.
Exactly. It shows that no matter how brilliant the software architecture is, no matter how elegant the discrete masked diffusion algorithm is, or how perfectly the L1 ABI manages the memory suitcases, it is ultimately completely constrained by the physical bandwidth of the hardware tier it runs on.
That makes a lot of sense.
It mandates a harsh reality check for the developers. You cannot deploy a bandwidth-heavy diffusion drafter on a memory-constrained consumer card and expect the 4x speedups you see in the pristine conditions of the lab.
It grounds the ambition in the cold reality of physics.
It does. It forces the developers to optimize the core integer math pipelines before relying on flashy architectural overlays. You have to fix the foundation before you build the penthouse.
This has been an absolutely unbelievable journey. We started down in the basement at the C-code border checkpoints, making sure memory suitcases were packed perfectly with inverted ownership flags so that the system wouldn't crash when a user hit cancel.
It's been quite the ride.
We explored the cyclotomic rings of the XBAR system, watching an AI struggle to hold on to its thoughts before the ink evaporated, and learning how they fixed it with replay decodes. We saw the immune system in action, proposing and gating memories, rewinding mistakes before they caused permanent brain damage, and having a philosophical debate about what is mathematically safe to forget.
All crucial pieces of the puzzle.
We translated the massive holographic alphabet of Gemma 4, and finally, we watched an AI use discrete mask diffusion to fast-forward its own thoughts, drafting the future while constrained by the cold, hard physics of an older gaming GPU. Which leaves me with one final, slightly provocative thought to leave you with.
I'm intrigued.
If we are truly looking at a machine architecture that can now use discrete mass diffusion to confidently and in parallel draft multiple futures at once, and it pairs that with an executive mechanism that perfectly consciously verifies those timelines against its own rigorous logic, while a background curator quietly manages a permanent episodic memory in the dead of night.
Where are you going with this?
Are we just building a really fast calculator? Or are we looking at a machine architecture that perfectly mirrors human subconscious intuition paired with conscious verification? The subconscious throws up a dozen parallel messy ideas instantly. The draft and the conscious mind steps in, evaluates them, and speaks the one that actually makes sense.
It is a profound structural parallel. We are moving far beyond linear computation. We are actively engineering a hierarchical, speculative cognitive loop that looks remarkably like human thought.
Something for you to mull over the next time you ask an AI a question and it answers you instantly. Keep asking those big questions. Thank you for joining us on this deep dive into the source material. Catch you next time.